Okay, any question about the previous session? Today we want to finish our discussion about GANs. In the previous session we talked about FGAN, which was constructed on top of F divergences. And today we want to talk about BiGAN and CycleGAN. Okay. As you may remember, we were looking for something other than likelihood to build our distance for learning the model. And we come up with a new idea based on a discrimination, a classifier for the data or the samples coming from the true data distributions and the data coming from the model you produced. And we see that the classifier that can classify these two, the best classifier that can classify these two classes can also learn your model. It's equivalent to a distance metric to learn your model. So this was our classification. This was the conditional likelihood of class labels, and we see that exactly this likelihood can be used for distance metric. And if you maximize that likelihood, that conditional that likelihood, the likelihood of your labels, it means that you have the best distance metric or the best critic who consider your work or check your work and your generation. And then we talk about the optimality. This optimality conditions show that how we can consider it as a distance metric. We see that if we have a model with enough capacity for the discriminator, then you are optimizing this distance metric. It means that you are optimizing the JST, which is a better distance in comparison to likelihood or Kabbalah divergence, which is used in the previous models. But we know that we are not doing exactly the same because you do not have enough capacity to put the discriminator as this ratio. Okay, this was the GANs training algorithms, and this was the attribute vectors and the mode collapse. And finally, we talk about FGAN. We have two problems in the previous sessions about the FGAN. Let me focus on those two. The first problem is how to derive GAN using the general formulation of FGAN. Okay, first pay attention to this G of F, which is equal to minus log of 1 plus and the other is this star, which is equal to minus log of 1 minus exponent. Now, assume that I replace these elements for the case of GAN. It means that apply this G of F and apply this F star to this formulation. What happened? GF of T phi. GF of T phi. So it is the minus log of 1 plus exponent of minus Tx, T phi of x. 1, 2, 3, 4. Okay, this is the first part. And also the second part is, so this is the first. The second is minus F star of G F of T phi of x. So what happened? First, let's focus on GF of T phi. GF of T phi equals minus log of 1 plus exponent of minus T phi of x. Now you should apply F star to this output. Okay? So minus F star of GF of T phi equals minus log of 1 minus exponent of T. T is this element. Minus log of, let's simplify it because you have exponent of minus log. So you can have it 1 over the exponent of plus log, and the log and exponent cancel each other, so I have just 1 plus exponent of minus T phi of x. Okay? So if you now replace this definition that we consider d phi of x as this term, you can see that both here you have, if you apply this minus inside the logarithm, you have this term, and also the second term, you have a minus behind F star, okay? If you apply this minus here, this minus term here is cancelled, and finally you will see that this term is exactly 1 minus d phi of x. Does it make sense? Okay, this was the first problem. The second problem was about the concept of when we are selecting T from a family, what happened? You know, the concept of lower bound here is a bit different. What happened? We know that, assume that this is the true distance metric to the F divergence, and we know that if we consider the complete family, we are exactly on the same curve because you are not the lower bound anymore. This is the case of when you have the complete family. In this case, when you limit your family, it means that you have some discrepancy, but based on the, for example, this is case 1, this is case number 2. But based on the size of the family you consider here, the maximum discrepancy between two functions is limited. You know? It means that if you consider a more complex, this discrepancy will be reduced, and the maximum of the discrepancy is limited. So when the discrepancy cannot be arbitrarily large, reducing this lower bound is exactly similar to reducing the true function itself. This is the difference with the general concept of lower bounds that you may consider here. So it means that they are stick together, they are bonded together, although they have discrepancy. One intuition for this paired curve is that if you start to increase the complexity, you reach the point that this discrepancy becomes smaller and smaller in the limit case. Okay, this was the concept of FGAN. Now we want to talk about bidirectional generative adversarial nets, or BiGAN. Okay, any question? Any question about the FGAN? Let me clear this part. We know that the GANs miss the density estimation task. We have three different tasks at the start of the course: density estimation, generation, and latent variable representation. We know that the GANs do not support the density estimation because they are likelihood free. So intrinsically, we cannot expect them to provide the P of X new. So this task is not available in the GANs. Generation, the generation is very simple in GANs, as they can generate samples in a likelihood free, so you do not need any restriction over the models you are using. So the generation is a great, it can be done in a great way for the GANs. And also the latent representations in the basic GAN that we talk about here, you can generate new samples using a latent variable z, but assume that you are given a true image from the data distributions coming from the data. We cannot talk about the, for example, any corresponding z to this x. Previously, in the case of VAEs, we talked about the approximate posterior that we show with q phi of z given x. And this was a great representation because we can talk about attribute vectors here. Okay? But here, we can, in the original GAN, we do not have any method to calculate the distribution over z or calculate z in a deterministic way. Now we want to talk about a version of GAN that can provide this path for you, how you can assign a z variable to each x you observe. GANs can provide latent representation for the generated samples, but they cannot provide representation for the dataset samples. Bidirectional GAN is a modification of GAN that can provide a latent representation for any sample. The concept is very simple. Assume you have two sources of generation. One source is your true data distribution, one source is the latent distributions. And you know that if you sample from the latent and pass it through your generator, then you have a sample from the true data distribution after training. But here we know that this is our generative model, okay? Now instead of considering g theta of z, which is x, I consider an extended vector, a concatenated vector, which is z concatenated to g theta of z, instead of g theta of z itself. Also, for the data coming from the true data distribution, I consider this architecture. First, I path the x through a new neural network. This is a new neural network, E psi of x. What happened? This E psi of x generates just about the dimension. The E psi of x is in the dimension of I don't know what happened, what we call the dimension of z, but it is in Rn, this is the dimension of z. It means that it generates a vector exactly the similar dimension as z. And then it again concatenates the E psi of x with x. So here I have z and g theta of z, and here I have E psi of x and x. And we know that both of them are the same dimension, because E psi of x is exactly similar dimension as z, and x and g theta of z are of the same dimension. Now what happened? The discriminator, instead of assigning a label value to each x or g theta of z, it assigned a label to the concatenated vector. What happened here? Instead of modeling the distribution, the discrepancy between the distribution of x and g theta of z, you calculate the discrepancy between these two joints. It means that when you, in the case of GAN, when you reach a point that a powerful d outputs 0.5 for any vector, it means that these two distributions are matched. Does it make sense? It is exactly the GAN. In the GAN case, when a powerful discriminator outputs 0.5, irrespective of the input, it means that the two distributions are matched. The minimizer of that classification error. You remember? Let me talk about that again. Consider this minimization. This distance metric, the maximum of this value. We see that if p theta and p data are exactly matched, or the samples are inseparable. When the samples are inseparable, it means that they are coming from the same distributions. They are equivalent. Then the discriminator outputs 0.5. It means that it cannot understand from which distribution the data is coming from, even if it is a powerful distance metric or is a powerful discriminator. In the case of bidirectional GAN, when a powerful discriminator outputs 0.5, it means that it cannot understand the discrepancy or the divergence or the difference between the distribution of these two vectors. It means that not only it cannot discriminate between g theta of z and x, but also it cannot discriminate between z and e psi of x. What happened in this case? Assume that we train the model and it converts to the best part, that a powerful discriminator outputs 0.5 every, independent of the input. It means that the distribution of these two is exactly matched, the complete vector. In other words, it means that if this is a true data distribution, if x is coming from the true data distribution, e psi of x is the corresponding latent. If this x is data generated using your model, this should be near to the z generating that x. Does it make sense? Yes? Okay. You know, you have two vectors that your powerful discriminator cannot understand the difference between them. So it means that it is just let's say I want to state the property in a more similar way as VAE. When the distribution of these two is exactly matched, it means that the conditional distribution, for example, of z given g theta of z and e psi of x given x is also similar. What happened here? Excuse me. For the true. What happened here? Here. Given g theta of z to you, because it is a generated sample, you exactly know the z. Yes? So, you know z. Here, you do not know what is the corresponding z given to this x, because it is coming from the true data distributions. But what you have here is exactly similar to the above. It means that what you have here is very similar to a z that can generate the corresponding x. So, using this formulation, you can easily, after training, pass X through E psi and then generate the corresponding Z. Does it make sense now? Okay. Yes.
So, I have a question from previous slide that if I understand that, I can understand that. So, why we cannot provide latent representation for the data set samples in the GANs?
You know, in the GANs, you just have access to the generator, to a generator, G theta. This generator is input with samples from the latent and generates samples for you, G theta of Z, that we call them X. But assume that you are given an X from your true data distribution, how you can reverse this process. This process is not reversible because it is not one-to-one, yeah. It is a very complex neural network, and you do not have the case of invertibility here, such as similar to flu models. Yes?
How do you get it? You just like randomly.
How we get Z?
Yeah, in that in the GANs.
This Z is sampled from the latent distribution. This latent distribution is generally a simple standard Gaussian distribution, and you sample from this standard Gaussian distribution and generate Z. I mean that PZ is fixed generally, it is not parametric.
Okay, so it's a count. Okay.
Yeah.
And why can't you like just sample Z into the generator to get an image, and then you just like do optimization with the target that you have to like get
yeah, that would be an option. You mean that put X here and start looking for a Z here that can generate that X. That can be an option, but the first problem is the complexity of the mapping here. But in the case of this network, if it converges to a point, then by passing through just one neural network, you have Z. It is much more simpler and efficient in terms of complexity and computation. And also, there may be some other problems because the inverse is not, you may have several Z corresponding to an input X. But we know that in the case of the true distributions, there is just one Z that is corresponding to your true data samples from true data distributions. And this procedure can find this.
So you say Z sample from, let's say Z sample from a normal distributions, right?
Yeah.
And then E of psi try to fit a normal distribution, right? Because Z is from a normal distribution.
Yes, and also it is much more complex than what we think. It does not just apply this to be a normal distribution. It also should handle the correlation between E psi of X and X, because it completely matched the distributions. Even the correlation between element of these two vectors, you know? It is not enough that E psi of X is coming from a normal distribution, a standard normal. It is not enough. It should come from a normal distribution that can, as a result, these two vectors are exactly matched in terms of distributions, you know? It is much more complex than just having a normal distribution over E psi of X. No, because the most important point is that it can handle the relation between the second part and the first part, because they are in a probabilistic model, they are related. We know that they are related.
So X is related to the G of theta down there, right? And Z is related to the E psi of X.
Yeah, this vector looks at this vector and wants to mimic its behavior. For this vector, everything is clear because you sample Z. Z is fixed, Z is generated, okay? You sample Z, and G theta of Z is a deterministic mapping. It means that for each Z, you have one X. Does it make sense? This vector wants to mimic the behavior of this vector. If it mimics, it means that for any G theta of Z in the first part, for any X in the first part, produce something that hopefully, if that things fit to the generator, should generate X again. Let's talk about this idea a bit more.
Then can you do KL between E and Z and the KL between X and G?
Yeah, it is in the virtual loss function. It is working on the JST of those two vectors. You know, because Z is generated, we know that this vector is fixed. Okay. Now just pay attention to psi. Assume that all other parameters are fixed. Okay, because all other parameters are fixed, including theta, this vector is fixed, just for simplicity. Now, I also have X because I sample it from the training set. Okay, if the distribution of these two is matched, when having X here, E psi should generate something here that mimic the behavior of the above. What is the behavior of above? One of the behavior of this is that if you input Z into the generator, then you output G theta of Z. Yes, this is the property of this vector. So your vector here, if converged, if learned, it means that a powerful discriminator outputs 0.5, it should provide you with the same property. It means that if it's output E psi of X here, and you input E psi of X into a generator, what will happen? What will happen here? What we expect to see in the output? What? No. This is of the dimension Z. And we know that everything passed through G of the dimension Z outputs something similar to dimension X. We hopefully observe X here. Why? Because the vector below wants to mimic the behavior of this vector. In this vector, if you input the first part to the generator, you will see the second part in the output. This is what exactly we want. If we input E psi of X into the generator, we see X in the output. So from now, I can consider this value as the latent variable corresponding to X, although X is one of the training data samples. And it is not generated by the model. We know that the samples generated by the model have their Z values. They are not the problem. The problem are X that do not have Z. But using this procedure, we see that E psi of X can provide the Z corresponding to X. Does it make sense? Okay? So, you know, matching joint is very powerful, let's say, you will be very powerful if you match this joint. It means that you understand the correlation between the parts, you understand the conditionals, you understand everything. You understand the joint. Yes?
So this joint, does this joint have a explicit formula that shows that these are two different things that are being joined, or just they're concatenated?
No, you know, each part is processed separately first because they are not of the same, let's say, content. One of them is from the latent, one of them is from the model. They are processed first, and at some levels they are concatenated.
And how does the model know where is the limit of, this is one module and this is another one, so find the matching between these two?
You mean the discriminator? Sure. The discriminator does not need to know where is which part is corresponding to data, which part, because it's observed two inputs, two vectors, and just want to match their distribution. It is not important which part is corresponding to data, which part is corresponding to latent. Yeah, because exactly similar to GAN. The discriminator can The most important property of discriminator is that it can match distributions based on data samples, not the likelihood. It is a metric that can match the distribution based on data samples, not likelihood. Okay, yes?
So the input of the P of phi in this case has a dimension of, for example, P plus N.
Yeah, yes.
0.
Yes.
So, and the parameter of the discriminator is phi, which can change the G of change the discrimination between these two samples. I think I don't understand how it can discriminate. So it can focus on making the x and the g of theta being very similar, but how it can focus on making the z and e of psi at the same time.
You know, you are looking at the problem in a separate way. These two vectors are not, the discriminator does not know that it, let's talk about this example. Assume that you have this vector if the distribution over x equals g theta of z and the distributions over z equals the distribution can we conclude the distribution of z and g theta of z equals the distribution of e psi of x and x? This is the important question. If each part, if the distribution over each part match, does it necessitate that the complete vectors have the same distribution? Yes or no?
Yes.
Yes or no? No.
No.
Yeah. You know, you may have a simple example. Assume that I have a Gaussian vector with two elements. Let's say z1 and z2. These two vectors can be, let me talk. This z is coming from a normal distribution 0 and 1, 0 and, for example, 2. Is it important that the correlation of these, how much is the correlation of these two random variables to form the distributions over the joints? We know that the distribution of the joint is a function of the correlation between these two random variables. You can check that. How the distribution over joint can be written as the correlation. You can write it as the rho value. Rho is the metric of correlation. Although they have exactly the same, let's say, a marginal distribution, but based on the correlation between these two parts, the joint can be changed. This is the important point. For a Gaussian, for a two-dimensional Gaussian, okay? This one can have 0 mean variance 1, 0 mean variance 2, but the joint can be totally different based on the correlation between these two random variables. This is exactly the same. How they are correlated is very important. You can easily find some E psi of x that the output is a standard Gaussian. But does that make the distribution of the joint exactly similar? Confidently, no. Just pay attention to the example of simple Gaussian. in these Gaussian distributions, exactly Z1 and Z2 are the marginal are this one and this one. But the joint can be really different based on the value of rho. Rho is the correlation between these two. When a model understands that these two vectors are similar, it means that their conditionals is exactly the same, their marginal is exactly the same, you know? Based on your case, assume that I think of, it's very, let me clear here, and then we can talk about maybe a more meaningful example. This vector, this is a vector coming from a distribution, okay? What is this distribution? Just to make it a distribution, this is Z, it means a random variable. This is Z0, one realization. I use Z0, pass it through the generator and generate an X, X0. What is this distribution?
Discriminator.
No. I want to give me a distribution over Z, given this G theta of this Z0. This is the distribution. It is a degenerated distribution. Why? Because just Z0 can generate this condition, nothing else. Does it make sense? You want to know what is the Z that generates G theta of Z0. That's Z0. Because just Z0 can generate that output. On the other hand, what is this conditional? When the joint match, the conditional also matched. But in the case that you talk about, when they are separately matched, it does not mean that the conditional is also matched. Maybe the correlation is different in the case of Z, two-dimensional Gaussian distribution. Look at the distribution of a two-dimensional Z based on the rho, based on the correlation value. You will see that how it can drastically change when the rho changes. It means that when the distribution of each part is matched, it does not, you cannot conclude that the distribution joint is also matched. Here, hopefully, when you have this distribution, then you have some degenerated distribution over E psi of x. It means that it generates the corresponding Z here, because the joint is matched and the conditionals are also matched when the joint is matched. So you have you observe the same degenerated value here in the perfect case, but you do not generally have something like that. And for example, you have something like this. You have a Gaussian distribution over Z, for example. But because you use a deterministic mapping here, this deterministic mapping exactly outputs Z0 for U. Maybe Z0 not, because do not conflict with the above one, Z1. It means that if you pass Z1 through the generator again, then you will observe X in the output, because the joint is matched. Yes?
So I don't understand why we should interfere the E of psi in the discriminator process. So let's assume that we created basic GAN model that we don't have E of psi.
Yeah.
And we have found the optimized theta and the phi values.
Yeah.
Okay. And then we generated autoencoder where the encoder is E of psi, and the question is what is the optimal psi in that case, and the decoder is exactly the G of theta.
The decoder is G of theta.
Yes. So we would like to find the E of psi model. So we would like to find the encoder model that transfer the X into the Z dimension. That if we use that Z, you get by the decoder, G of theta as a decoder.
Yeah.
And if we use the G of theta as a decoder, we come back to the X.
Yeah. That's a similar concept to what we have here. It is not different from here. Why? Because when you use that autoencoder, you said that I input X into an autoencoder. For example, this is the encoding layer. I have some X. I have something here like E psi of X, and also impose that the distance between, you should apply this, the E psi of X and PZ minimize, because you want to be the same. And then I use a decoder to output X here. In this case, you are using the condition. It is exactly the conditional distribution, this part. Conditional Z, you want to generate exactly the X. In that case, you follow the relation between the two parts, you know? But in the case, I just assume that you pass X. The thing that we talked first was that if you pass X into something that in the output it generates E psi of X, and this E psi of X is coming from PZ of Z, it is not enough. It is not enough that you generate a mapping that its output follow your prior distribution. It is not enough. If you have something that again map the code or the E psi of X into X, it's okay, because you are using the condition. Yeah. But this is not enough, that you find the distributions that make the distribution after passing X through that transformation, you have something that is coming from the latent distribution. It is not enough. It means that you are just matching each of them separately. You are not having the correlation. The correlation is missed. But all the information is in the correlation, because the correlation shows that this Z is corresponding to this G theta of Z. Does it make sense? Clear? Yes.
So I understand it's the same, but in the one he talked about, though, it's not going to be likable free, right?
Yeah, that's a mixture of VAE with GAN, something that he talked about. But it works because you use the conditional. It means that you are again using the joint. Yeah, that makes sense. But the problem was this scenario. This scenario is not working. Although the output, you can find different E psi that the E psi of X is coming from the latent, your latent. But they are not. All of them are not your transformation. Your transformation is the one that you cannot discriminate between these two vectors using a powerful discriminator. Okay? Clear? So, but after the class, pay attention, check that Gaussian example. You can write the joint of a two-dimensional Gaussian as a function of rho. It means that although conditional distribution of each element is exactly similar, but when the rho changes, the joint will be changed. It means that the correlation between the parts is very important. Yes.
So like all encoders is learning like the marginal, right, and the conditional. So
the conditional. Okay. The autoencoder is learning the conditional marginal. Yeah.
Okay, then the for BiGAN is learning the joint distributions, right?
Yeah, it's a much. You know, the joint is everything. When you have the joint, you have the conditional. You know, because you can marginalize out one part, and then the ratio is the marginal, is the conditional.
So is there a case that we are trying to learn like length rather than like conditional?
Yes, exactly. We want to learn the joint.
Okay.
And assume that the model is fixed. This vector is, the distribution of this vector is fixed. You want to change psi so that it mimics this distribution. Because we know the z corresponding to gen samples generated by the model, so if the model is fixed, this distribution is fixed, just for simplicity, okay? Then you change psi such that this concatenated vector mimics the behavior of this vector. So it means that it learned the joint here. And when you have learned the joint, it means that E psi of x is exactly similar to z, both in marginalized distributions and in conditional. It is much more complex than just marginalized distributions are exactly the same.
So E psi doesn't learn conditional, right? It's learning the joints.
E psi and x is the joint, okay? I learn the distribution over this joint. Then I can have both the distribution of E psi and each of them separately, they're conditional, because I have the joint. Joint is the more complete distributions, the most complete distribution that I can have. Okay, so after this discussion, if I input x, what do you think of this transformation? Assume I have x, then I calculate E psi of x, then I calculate g theta of E psi of x. What do you think what happened in the output? Hopefully x. Yes. It means that it can, to some extent, it can inverse the E psi can inverse the operation of g theta. And this is what happened in practice. These are samples generated using GZ. It means that when you learn the joint, you have your generative model working very well. It means that you can put it aside and use it as generative model for sampling, and it works very well. But you have also something like AE that can generate the latent for X. This is data set samples. You pass it through your E, and then you pass it through G again. And hopefully you see exactly the similar image. But now you have E of X. And E of X is the latent representation corresponding to X coming from the true data distribution. So you have latent representations for your dataset samples, which was missing in the original GAN. Okay? Yes.
Can we say that the cost of making a GANs bidirectional makes the generation process worse, not for money, but the generated output of BiGANs are worse than the GANs?
Generally, if you add enough capacity, because you must make your discriminator more powerful. The discriminator now wants to discriminate between two higher dimensional random vectors. I think if you provide them with enough capacity and also data, then you have exactly maybe the same. Because the objective of showing GZ here is that you have your generative model working very well, but also you have E of X.
But the GANs are at least the same as BiGANs.
Yeah. If you limit, for example, the data, that GAN should work better in generation. So this can be applied to more complex data set. For example, over ImageNet data set. These are GZ, and you can see that they generate meaningful images. And after using GE of X, you see that the concept is the same almost. The concept is almost the same, but you have some discrepancy between these two images. But hopefully, if we observe exactly the same, we can claim that we recover the latent variable distribution. Yes.
Can you explain why we need to know the Z, like how it's gonna help us?
Generally, generative models, in addition to the generation part, when you have Z, for example, in the case of attribute vector, we see that attribute vector works for GANs too. Attribute vectors, when we talk about attribute vectors in Z, I said that assume that this image is generated using the model and we have access to Z. But in general case, you have X. So you cannot work on X and attribute vectors if you do not have this E of X. Because you should have some means to go to the latent space, and there you can design the attribute vectors. What we talk about, now I can update my description about the task of attribute vectors. How? Now I can say that assume, in the previous, when I was talking about this idea, I said that assume that Z and W is generated first and then you have this image. Now I can say that you have this image, you have a BiGAN, so you can generate its Z and W. Latent space is much abstract and it is more informative and it is lower dimensional. It is a bottleneck of information, so the information there is very abstract. For example, if you apply a simple, let's say, clustering algorithm for Z coming from MNIST, you will see that they can be easily discriminated in the Z space. Z is a higher level information of your data, and that's very useful in some tasks. Any question? Okay. This was by GAN. These are again ImageNet, and now we want to talk about CycleGAN. CycleGAN is the last part in the GAN architectures, and after that we will go to the energy-based model. Yes.
Is there a reason we use BiGAN for like a representation learning than like VAEs?
BiGAN was, I think, BiGAN was proposed to solve, because GANs can generate very high quality images, okay? So they can be used in practice, but the part that they cannot provide you with latent representation was a missing part. So it was let's say, it was a try to add this feature to the GANs. Nowadays, generally, the original GAN is used because GANs are targeted for generation, not the latent.
I see. So like VAE is more suitable for like learning representations. BiGAN can say this or not?
Yeah, to some extent, but the VAE backbone is based on the likelihood. It is likelihood free. There is some differences, yeah, but in the performance side, yeah, I think the VAE can provide better latent representation. Yeah. And one important point about both GAN and VAE is that both of them in the latent space you can find attribute vectors. In the case of Lu models, I said that finding the attribute vectors is hard because the dimension is exactly the same. You have not the bottleneck of information and something like that. But for both GAN and VAE, you have this bottleneck, and both of them are powerful in the case of generating attribute vectors in the latent. Yeah.
I see.
Yeah. The example we had before was the attribute, for example, for smile. So what is a CycleGAN? CycleGAN is an attempt for providing GANs and working on conditional distributions. Now we will see how you have conditional distributions in GAN. Okay, assume that you have a paired data set. These are a sketch of shoes and this is the realization of that sketch. Okay? And they are paired. It means that you have access to each of the pair separately. And you want to find a mapping that map xi to yi. So you have an image-to-image translation with paired data set. It means that as you have access to this paired data set, xi are sketches, yi are object images, or xi are grayscale images, yi are color images. The objective is to find two mappings. First mapping is a mapping from x to y such that if you input xi to that g, then you have yi. And also f is the reverse mapping. This work can be done using different supervised setting. Why? Because you have the paired data set. Okay? Now we want to make the task more complex. You have access to unpaired data set. Okay? Assume that you have access to paintings of painter number 1 and painter number 2. They have their own method of painting, so you can, one professional person in painting can easily understand that, for example, this painting is from the painter number 1, this painting is from the painter number 2. You have a data set of painting of these two persons, these two people. What happened? You want to find a mapping here that when input with a painting of coming from X, it generates something from Y. Let's clarify the task. The CycleGAN, primarily known as Cycle Consistent Adversarial Networks, is again an image-to-image translation, but it is unpaired. So what happened? You have access to this data set. Pay attention that you do not have the paired data set. You have some xi that are coming from one of the painters, and yi's that are coming from the other painter. In this case, so you have two different distributions. The first distribution is the distribution of the paintings of painter number 1. I denoted by p data of x. Why p data? Because it is real world data. And why x? Because it is corresponding to painter number A. And also for the painter number 1. Painter number 2 have the y distribution. What is our task? The task is as follows. We want to find a mapping such that if you pass xi through that mapping, the resulting output resembles data coming from p data y. What happened? Let me talk about the shoe. Assume that this data set is not paired anymore. You have the sketches in one part, you have the shoes in another part. Now, if I give you a sketch of a shoe, you should give me the corresponding shoe. But you do not have access to the paired data set in your training data. You just have some sketches, you have some images of shoes. Yes?
So, second example of that, something like style transfer.
Yeah, that's exactly like a style transfer in an unsupervised manner. We have a style transfer in supervised manner, we have a style transfer in unsupervised manner. It is style transfer in unsupervised manner, yeah. In other words, you have the style of this data set is sketches, the style of this data set is real world images. Now I give you a new sketch. I want you to give me the corresponding shoe image, okay? Without having access to the paired data set. This is the important part. But this task can be restated as a GAN task. Now we want to talk about how we can restate. This can give you some intuition. Assume that I want to find a G from X to Y such that GXI resembles this data set, this distribution, sorry. In other words, a powerful discriminator cannot discriminate between GXI and data that are coming from Y distribution. In other words, a person professional in painting, if you give this painting, you have a painting from painter number 1. If you give it to your G, the result is something, we call it P prime. A professional painter cannot discriminate between these two paintings. He cannot understand that it is a transformation of other painting or no. It is exactly one painting from the painter number 2. In terms of distributions, you cannot discriminate between GXIs and the data that are coming from P data Y. We have some samples from this distribution too, YI. You have the unpaired data set, so you have XI and Y. Okay? And also on the other hand, you have a mapping F such that when samples from Y random vector pass through that F, the resulting data resembles P data of X. It means that from the other side. If I pass a painting from painter number 2 from the mapping F, the resulting image is something similar to the painter number 1. And a professional person cannot understand the difference.
So the discriminator knows the pairing, right?
No. The discriminator does not know. It means that you do not need them to be exactly similar in content. You just want this P prime to be coming from the same distribution as P2. You do not want the content to match. It is not important. You just want the distributions to be the same. Yes?
How does a discriminator go to just detect the distributions match, not the content?
Yeah, that's the likelihood free divergence metric. The likelihood free divergence metric says that I can compare the distributions based on the samples from them.
Okay, so when you compare the samples, it means you compare the content.
No. Pay attention that you are not working with the divergence that take the difference of two images. It is working on the distributions. It means that the content can be different, but the distributions can exactly match. It means that in the distribution of P data Y, this point is in the point that you have several points of Y, that high probability in Y. It is not important what is the content. It means that this, if you give it to the P data of Y, it gives you high probability. This is important, not the content. This is the task that we follow in likelihood-free divergence metrics. They compare the distributions with just samples, not the likelihood. Yeah. Let's talk about this further. I think it can solve your problem. Now I want to design a G mapping. Okay, what was G mapping? The G mapping was a mapping that when you pass X through G, we will talk about the content, how you will preserve the content. But although you preserve the content, the style should be transferred because you want it to come from the other distribution. Mapping G. Now we want to design mapping G. We know that mapping G is something that when you pass X through G, the resulting samples must resemble P data Y. Equivalently, a discriminator dy cannot discriminate Gx and y. This is exactly what happened. A professional painter cannot discriminate whether this painting, which is a transformation of painter number A, is really a painting of number A. It is exactly similar to the paintings of painter number 2. A professional painter means a powerful discriminator. Okay? So what is the loss? It is exactly the problem of GAN. One side is exactly the problem of GAN. How? I want something that that if y is coming from the true y distributions cannot be separable with samples coming from x distributions but pass through gx. Just replace x with z and y with x. It is exactly the GAN. Nothing different. Just pay attention to your sources of data. P data of y. You can sample from these distributions because you have unpaired data set. Unpaired data set, it means that you can sample from each of them separately. And this is what GAN can handle for you. These samples must be inseparable from these samples. For inseparability, a discriminator should not understand the difference between the vector distributions. So I just need a discriminator here. For this case, I denoted it by dy. Does it make sense how this loss can match g of x with y distribution? Just pay attention that your prior is not a simple Gaussian distributions anymore. It's the p data of x. Nothing changed. Now other side. I want to design f. This is the first part. Also, I have a second part. You have samples from these distributions. Also, you apply f to y, and you have f y here and x here. Again, you do not want to see any discrepancy between these two vectors in terms of their distribution. So, a powerful discriminator that we denoted by dx. This is a separate problem. This is the first, this is a separate problem. You have exactly this loss. This is exactly the same, just x and y are changed with each other. Here it is very simple. If you replace any y with z, you have exactly the same loss as GAN. Okay? So, I want to this two transformation. One transformation matches the distribution of x with y. The other one matches the distribution of y with x. Now, if I train these two transformation, I minimize the f and g such that the GAN of both of them is minimized, then you will see something that that in the output, for example here, if you train the model, in the output you have f of y, and f of y is distributionally exactly the same as x, and also g of x is exactly the same as y. But what's the problem? There is still a problem here, because these transformations are these transformations have high capacity. They can generate samples irrespective of the input. What happened here? They can generate samples. The content is now appear in the loss function. Because this f has a high capacity, it can generate f of y irrespective of y. It means that it can generate something like f of nothing, and this f of nothing is exactly matched to the distribution of x. It means that it minimizes your loss function, but it is not dependent on y. Why? Because it has high capacity. It can, for example, generate samples of pattern number 1, irrespective of what is in the input. And also G. Now, you add a cycle consistency loss to this loss function. And what is that loss? That loss says that if you transfer x using G to the distribution y, it means that y hat is exactly the same distribution, is coming from the same distribution as p data of y. Then if you inverse your transformation using f, you have x hat. The consistency loss necessitates that this discrepancy between x and x hat should be minimized. It means that the f or g cannot generate samples based on their capacity. They must pay attention to their inputs because they need to reconstruct it in their inverse. And also the consistency in y, both of them.